The mathematics of lenses. Using a convex lens, it is possible to create an image of this monkey. The question is, where will the image appear? Now there are two ways to solve this problem. The first with a ray diagram, the second with a calculation. Let's have a look at both. Using a ray diagram first. Construct the image of the object formed by the convex lens. We can do this using the three principal rays. The first parallel to the optical axis through the focal point, the second through the optical origin, which continues in a straight line, and the third through the focal point, and then it is refracted parallel to the optical axis. Now you can see that the three rays meet in the same point approximately. This is a problem because we do not know the exact size nor the exact height of the image. Therefore, we can use a formula. There are two formulas you can use to solve numerical problems concerning lenses. The first is the lens equation. 1 divided by the focal length equals 1 divided by the object distance plus 1 divided by the image distance. The second equation is the magnification equation. The magnification equals the image height divided by the object height, which equals minus the image distance divided by the object distance. Now remember that what these things mean. We've got the object distance, the distance from the object to the lens. We've got the object height, the height of the object or the length. We've got the image distance, the distance from the image to the lens, and we've got the image height or the length of the image. Example 1. A 6 cm tall pencil is placed in front of a convex lens at a distance of 20 cm. The focal length is 8 cm. Calculate the image distance and the image size. Now first make a sketch. And because the pencil is outside the focal point, we know there is a real image on the other side of the lens. Now fill in what you know. Now the image distance and the image height are unknown. It is convenient to write down the two formulas. Fill in what you know. And you can use a calculator here. Now we need to subtract the 0.05 from the left hand side, which gives us 0.075. So the image distance is 1 divided by this figure, which equals 13 centimeters. Now what about the image height? Again, fill in what you know. Now use the second equation, the magnification equation. So the image height is minus 4 centimeters. Now this minus 4 centimeters indicates that the image is inverted, that it is upside down, and the minus 4 centimeters is a height below the optical axis. This is what you get for a real image. Example 2. The pencil is moved towards the lens such that the object distance is now 7 centimeters. The focal length is still 8 centimeters. Again, calculate the image distance and the image size. Make a sketch first. Now remember that now the object is within the focal distance. This means we'll get an upright virtual image on the same side of the lens. Again, fill in what you know. Now the image distance and the image height are unknown. Write down the formulas and fill in what you know. First, we will use the lens equation. Use your calculator here. And these figures are rounded off, but not in the calculator. We need to subtract the 0.143 from 0.125, and we'll end up with a negative number. Now the image distance equals minus 56 centimeters. And the minus indicates that the image is on the same side of the lens as the object. What about the image height? For this we can use the second equation, the magnification equation. The two minuses cancel. Use your calculator here, and you will end up with a image height of 48 centimeters. Because it is plus this time, we know the image is upright, above the optical axis.